Oh, there you are. Okay, so this is your lapel mic. It's already.
Oh,
I will.
okay.
Go ahead and connect more. And what I'm going to do is I'm going to go on my phone, look up on YouTube, and then when I tell you, I just want you to do test 1, 2 into the mic, and I'm going to see if the camera's picking up.
Yeah.
And that's it. So we should be good to go.
Okay.
All the RSVPs were already emailed with the link to our YouTube channel, and everybody. There were people who tuned in to Misty's talk.
There's a big problem.
Yeah.
So you need to hook your laptop up to the HDMI.
Okay.
Right?
Yeah.
Because it's not showing.
Yeah.
Right? So
so your presentation I'll share your screen so that for people tuning in, 3/4 of the screen will be your presentation slides, and then you'll be in a box in the bottom right.
Okay. All right. Is this it? I think it's it. All right. You finished?
Yeah, I don't know if you can go in there.
Maybe. Yeah.
No, we already got
Already.
Yeah, so anybody who's new.
Okay. Okay, it's up.
Great.
Oh man, why is it doing the flicker thing?
It kind of adds to the ambiance. Okay, so now we're going to share.
Yes. Yeah. Can we turn down the lights just a little? Because it's not looking good. Yeah.
To actually be able to see this,
Yeah.
probably need them
Fully off?
That's what I usually do for presentations. I can dim this a little bit up here, but it won't get much dimmer than this.
Could we put the lights on?
That's as dim as it goes for the top.
Oh, that's okay.
Turning these off. This is okay?
This is okay, yeah.
Okay.
I want lights
if you
on.
change your mind, then just let me know to hit off. Or
Yeah.
Okay.
Yeah, I would prefer to have lights on.
Okay.
Than not have lights on. Yeah. Yeah.
Oh, in the front. Hodari-Sadiki, Hubbard-James. Cool. I'll probably call you Dr. James for short for most of
Yeah, that's right.
But did I say it right?
What? Hodari-Sadiki? Yeah. Oh, I
I
didn't realize you. I was like, why you can't say my name?
I'm saying the whole name.
Like, you know me. Like, why you say my entire name? But I hear you. I get it.
What did you guys end up saying to that LA guy?
Oh, next year, yeah. What's he doing?
That's generous.
I'm glad you came in. You're just in time.
You're just in time.
I'm goaded.
I'm gonna get out of
You
there.
can attest to that.
Okay. Ready? Oh no! Wait, that's just the. That's not it. It's this one. Yay! Does it do thing? Thing do?
Oh, because I'm in the square thing. It's my phone.
Go.
How long is your show?
It's going to be like 30-minute stops. That was the plan, right?
Okay,
yeah.
that's what I thought. Just double check.
Yeah.
Okay, this is our sky. Perfect.
All right. Because you're jumping in after me, right? Yes.
Yep.
Okay.
So, baby, you'll notice that I've been here and not cleaning up our home. Aditya's flight was delayed, so that's why that wasn't.
Okay, that's fine. I got introduced to her.
For sure.
Yeah.
When does this night flight forward? When do you get
Okay.
Okay, so he'll be there when you get home, just like.
Okay.
And I'll be leaving early to take it. Okay,
Give us a little bit of time. I think he still wants to test the sound.
Oh, okay, sure.
Yeah. Oh, I think I can hear me.
Should we use the mic within here too, or does that amplify it?
That's a good question. I don't want to do two.
Yeah,
right, because it's going to interfere. I think they'll hear me fine in here.
Okay.
Yeah, that's why I'm trying to save my voice. Right, yeah. I'm going to sit down next to you, Lauren. because I gotta conserve my energy for this talk. I try to get super lazy right before I talk because there's so much energy that I expend in the talk, and then I'm just like finished. Yeah, I'm just tired. So I'm like, let me give it a little time. Let me give it a little time. Let me give it a little time. Yeah.
How much of a drive is it? Or are you gonna take a bus?
And are you what major are you? Or what major are you thinking of being? Because you're a first year, right?
No,
Mhm.
I'm actually technically going into my junior year,
Okay.
but I had to take off last semester.
Okay.
Yeah, but I'm doing the middle degree program for computer engineering.
And okay.
But at Agnes, I'm also studying political science.
Okay. So you're doing Emory?
Um,
The Emory
Tech.
thing? Oh, tech. Okay.
Yeah.
Mhm.
Emory's computer science.
And this is computer engineering.
Yeah.
Okay. All right. All right. So it would be, so you're going to engineer. So it would be at the end of this year that you would transfer.
Yeah.
Okay. All right. Yeah.
Could you walk to the front?
And then talk.
I'm just testing it.
Yeah.
This is what you look like right now on YouTube.
All right. That's not the faulty. Testing, testing, testing. Can you hear me? All right. Good. All right. Are we ready? We ready? I'm ready.
All right, let's do it.
Oh, clicker. Clicker. I need a
Alright,
clicker.
hold the clicker.
Yeah, hold the clicker.
Right to go right, left to go left. And then the main middle button, hold down, that's laser.
I can't take a flash photo of the speaker.
So I will never have my full screen.
That's about as full as I can make it. Because it's Google Slides, and I can only share a tab. I can't share the whole thing.
3 dots. That thing, the square.
Well, that's so this is full screen.
That's the screen?
Yeah.
Oh man. All right.
There's only so much I can do.
Yeah, right. All right. We ready? Everybody ready? People coming in? Yeah, let's go. All right.
Hello, everybody.
Hello.
Welcome to our very special summer show at the Bradley Observatory as part of AsTropaLooza. Usually we don't do shows in the summer because usually we're just during the school year. So yay, summer show! It is my pleasure to introduce our speaker tonight, our very own Professor Dr. Hodari-Sadiki Hubbard-James. Dr. James for short.
Yeah.
Dr. James studies orange stars. Yes, some stars are orange, and those are the ones that he studies a lot, as well as exoplanet implications. So Hodari's going to tell you all about the above. Please take it away, Hodari, Dr. James.
All right. Good night, everyone. Are we happy to be here? All right. Good. So this is something new for me. I've been giving talks and doing lectures for over 10 years, and I like to do it. I like to think that I'm also really good at it. Hey, we'll see. But today's the first day where I'll be doing an experiment while giving a talk. Okay? So I am a little nervous about doing this by myself. So I'm going to have 2 people come up and help me. Not right now, but you'll see them in the crowd. Charlie back there, and is it Jacob? Is Jacob? All right, and Jacob over here. So they're going to come up at points in the talk to like give me a helping hand, okay? And also, this talk is going to be shorter than usual because Lucia, can you do the door for me? Yeah. It's gonna be shorter than usual because we had it planned to be like a short little 20-minute talk, 20 to 30 minutes, and then you will be wowed by Dr. Alex Yep that just introduced me with a planetarium show, okay? So we're going to turn all these lights down and we're going to bring the stars up and you're going to like go out, figuratively speaking, you're going to go outside and experience the beautiful universe and everything that we have to offer here in the Bradley Observatory. Okay, So let's get started. Let me read to you my talk title. So, From Earth to Exoplanets, how scientists are searching for life. Okay. So let's talk and start with talking about me. Does anyone recognize the beautiful flag that? Sorry, thank you, thank you. So if you can hear from my accent, I am from Jamaica, right? Born and raised. I came to the U.S. in I did all my K through 12 in Jamaica. I came to the US in 2008 to do college at Berea College, which I think is the best. Sorry, not the best. Agnes Sky is best. Maybe the second best college that we have in the US. So I did my bachelor's in physics at Berea College. Then I went to University of Cincinnati and I got a master's in biomedical engineering. Then I went and worked as a biomedical engineer for a little bit. And then I came back and I did grad school again, and I got a PhD in astrophysics, astronomy. Okay, and this is why I'm here and talking to you today. So now I am a assistant professor of astronomy and physics here at Agnes Scott College, right? And I've been here for a little over 2 years now, and really love it here. The students and all of the observatory and staff have really grown on me. What am I interested? What's my motivation? Why did I go back to school again after having a nice job here in Atlanta? Because I am interested in finding extraterrestrial life, astrobiology, which we'll talk about a little bit more. So if you don't know about astrobiology, we'll learn here, and habitability. One of the big reasons why I went back to school is to merge my experience with biology and my new knowledge of astronomy, right? And that's what we're going to do with our experiment today. So before me, people who are in the room, you can see the cups. You have A, B, and C. And I'll give you a hint. There's life in one of these cups, right? They look completely identical, but there's life in one of them. I'll give you another hint. In every cup, there is sand, very expensive sand, but sand nonetheless, right? And in order to figure out what is in these different cups, you'll see that if you look at them just by eye, you can't really tell what has life in it or not. And I'll ask my first uh, helper volunteer to come up. I'll ask Jacob to come up. Can you come up, Jacob? And Jacob is going to be our eyes and ears and everything for this experiment. And I'm going to ask Jacob to look in all three and see if you can see any difference. Mhm. You think that's one? All right, all right, all right, all right, all right. That's good. Like, you can go back. We'll see if you're right. So Jacob said A. Who agrees with Jacob? All right, just on base. Good, 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 good. I like to see it. I will tell you that I don't even remember what cup it is in. So it's good. So what does life need? Okay. So the three things that life needs is number one, you can see it right there, you can shout it out with me, is water, right? So it needs water, it needs an energy source. And in generally it's the sun. If you're looking outside of our solar system, it's some other star. If you're on a planet where you're like deep in the ocean, you would look at that energy source being a geothermal vent or something of that sort, right? So you need some energy source, and you also need chemistry. You need building blocks. You need things to like actually bond together in order for the life to be, right? To exist. Okay. So next, I have to introduce what is astrobiology to you, right? So astrobiology is basically the scientific search for life in the universe, both in our solar system and outside of our solar system, right? And it means that in our solar system, are places that we can actually go and try to find life or try to like touch the life that's there. But outside of our solar system, we cannot do that. So we have to come up with more interesting ways of searching for life around exoplanets and others, or on exoplanets and around other stars. Right? So the scientists are looking for life on planets and moons in our solar system, on distant worlds around other stars, And also, we're not going to talk about this today, but I had to put it on, listening for intelligent life. So the search for extraterrestrial intelligence, SETI, right? We have, quick shout out, we have a student from Agnes Scott working with SETI this summer doing research. So yay, she's going to find life and come back here and tell me, never mind. But this is the ways that we look for life, right? So today's big question is, how do we tell if something is alive? So Jacob just now looked in cup A, and apparently Jacob saw something in cup A that said maybe there's life in cup A. Okay. Another way that you could do it is by using your other senses, right? What other senses do we have? Touch. We're not going to touch the cups or stuff in the cups today. You can smell, right? You can hear what happens, right? So we're going to use all our senses when we're trying to figure out what cup has life. Okay. All right. So there's a little tree cup thing. All right. So the habitable zone, right? So for something to be habitable, you need all of the things that I said before. But for a surface to be habitable, what's the number one thing that we need? Water. All right. Yeah, we need air as well. We need thing, but we definitely need water. So the habitable zone is defined as the region around a star where you can have liquid water on the surface of the planet. Okay. And you can see in our. Are you good? Okay. It's good. Okay. Yeah. You can see in our solar system there are two planets that currently reside in the habitable zone. Right. So it's Earth and Mars. Okay. Or is there life on Mars currently? No. Do we believe that, or do we think that life could have existed in Mars in the past? Yes. Okay. Yeah. So the first question, and this is not a class, it's not a class, but I am a professor. And the reason why I became a professor is so I could give out quizzes, right? That's the whole reason. So my first question, right? I think my only question I have for you today, you're lucky, is can life exist outside of the habitable zone? Yes, I hear a yes. Yes. No. In our solar system, can life exist outside of the habitable zone in our solar system? Who says yes still? He says yeah. You say, all right, we have people that say yes. You're very confident with your yes. Where can life exist outside of our habitable? You went for you could have just said the moon, like you don't have to give. All right, yes, yes. So it can exist on the moons, right? So Europa is a moon of Jupiter, right? One of the four Galilean moons of Jupiter. I'm going to teach you something real quick. This is was not planned, but how I remember, and people who have had someone's class will remember. How I remember the four Galilean moons of Jupiter is I eat green cats. All right. Say it again. I eat green cats. All right. So I is for Io, right? E is for Europa. G is for Ganymede. And C is for Callisto. Callisto, right? Yeah. So I eat green cats. Remember that. That helped me to pass so many exams. Thing. So yes, it can exist outside of our habitable zone. And my favorite moon that exists in our entire solar system is Enceladus. It's a moon of Saturn, and it has these very peculiar things. You can see them right there. Let me see if this works. Right? These tiger stripes, right? And it's expected that just like Enceladus that you just told us about, it has a subsurface ocean where you could possibly have life existing under the surface of the moon. Okay? All right. Good. So we just talked about solar system. So the search for life, you can have life in the solar system, and there's three different ways that we study this. The first one is by looking at life here on Earth, right? So looking at extreme life and seeing if that extreme life could possibly exist in the most extreme conditions that we would find on other planets. The second one is by sending rovers. So we have the Perseverance rover right now. Oh yeah, you can come in. Yeah. We have the Perseverance rover that is currently on Mars and is collecting samples for a sample retrieval mission that should be scheduled for late 2020s. where we have fingers. Thank you. Yeah, cross those fingers. So where we would go and pick up those samples and bring them back to Earth and see if we can find signatures of life from the past, right? And the third is I have here Europa Clipper that launched in 2024, and Europa Clipper is meant to study Europa and look for life underneath the ocean or underneath the ice in that subsurface ocean. All right, so we're back to our experiment. We just had a lot of conversation about what molecule, what thing, water. Who said it? Someone said it. Someone said water. You said water? All right. So we just had a conversation about water. So what would we want to add to our cups right now? Water. All right. So I'm going to have my second Charlie. Can you come up here to help me? I'm not going to have you pour the water, Charlie, but I'm going to have you observe from like right up close the water. Ready? So I'm gonna pour it in A. See what happens. You see anything? Not really? All right, let me do the second one. Not really? All right, ready? Ooh. Okay.
That one came with smoke.
Huh?
That one came like
Smoke? Yeah.
Yeah, it has smoke.
It had smoke. Yeah. Okay.
It has smoke.
All right. So Charlie said nothing in one, nothing in two. Check all of them again just to be sure. Nothing.
No,
What you saying too?
no.
No.
Then this is like stuff like here.
Okay. All right. I'm bubbling, right? Okay. All right. All right. So Charlie says, Charlie, which one has life in it? The bubbly one. All right. Which one do you think, Charlie?
I think it's the bubbly.
It's the bubbly one. All right. So no, we have Jacob saying A. We have Charlie saying C. Who is for A? Put your hand up and give Charlie a round of applause and Jacob as well. Thank you for helping me. All right. How many people for A? Huh? Yeah. Yeah. I agree with you. I see. I agree. Who says A? All right. Who says B? All right. Who says C? All right. All right, for play. All right, let's move on and come back to our little experiment a little later. All right. So next, let's talk about life, and we have more entrants. Let's talk about life that is around other stars. Okay. So this is the type of life that I really enjoy. Right. That's where I do my research. So we have two things right here. We have the transiting Earth telescope, right? We're transiting Earth satellite, right, test that is searching for exoplanets around other stars. And we also have the James Webb Space Telescope that is characterizing atmospheres of these exoplanets. All right. So we're going to talk a little bit about both of them in these next couple of slides. So first, in order to find this life, you have to find the planet, right? And in this slide, you see that we've found so far using different methods, 11 different methods, we've found 5,921 exoplanets orbiting other stars, right? And the two main ways that we detect exoplanets is one, by using radial velocity, and this is a hark back to the best telescope in the world, right? The 1.5 meter in Chile with a Chiron spectrograph, and this is what I use to do my dissertation and get a PhD, so that's why I love it. It doesn't have to be your favorite. However, give it a round of applause. And what Chiron does is it finds exoplanets using radial velocity, right? And what radial velocity is the wiggling of a star, right? So a star, when it has planets around it, just like our sun, it moves back and forth slightly. And if you look at the different wavelengths of light of that star, you will see that those spectral lines, I'm using some big words, go back and forth, right? Basically in periodically, like over many years, just how our Earth, our Jupiter goes around our sun, right? So if you see your star wiggling, you can surmise that, oh, it must have something around it like a exoplanet, right? So using this method, we have found 1,126 exoplanets as of June 11th, 2025. And I took this data from the NASA Exoplanet Archive, which is a great resource for anyone in the public to go and check how many exoplanets we found so far. And the second method that we use is the popular one, right? It is transit. It's the transit method for looking for exoplanets, right? And with the transit method, we usually use space telescopes. So you have Tesla already introduced and the very popular and now not so much in functional Kepler space telescope. And both of those look for dips in starlight, right? So whenever your planet transits or moves in front of your star, there is a reduction in starlight coming from that star, right? And if you keep your telescope looking at that star, you can see these dips or these transits, and you can see that, oh, there must be one planet, there might be two planets, there might be three planets even going around this one star. And this method has been really fruitful for astronomers, and it's found to date 4,387 exoplanets orbiting other stars, right? There is a discrepancy between the 4,000 found here and the 1,000 that we had on the previous slide. Somebody did the quick math, right? Not me, but somebody did it. And it doesn't add up to the 5,921. And that's because we have so many other methods that people use, such as direct imaging, which is where you look directly at the exoplanet and try to see that, confirm that it's there. You also have gravitational lensing and astrometry, which is very cool science that you should all grow up and want to do, but we're not going to talk about it today. All right, so now you found the planet. How do you find that there's life on the planet? Can we go there and visit the planet and drop a rover on it and look around for life? No, we cannot, right? So this is where James Webb Space Telescope comes in, where James Webb looks at the longer wavelengths in the infrared, and it does this cool thing called transit spectroscopy, right? So we all know, someone said it, who was it that said oxygen earlier? You said yes, and you felt like you didn't get it right, but you were there, right? Because in order to have life, usually life affects the planet, right? We affect the planet. We were terrible for the planet, but we do affect it. So if you are a scientist on around another star, on a planet around another star, how would you see that we are here, right? We put things into our atmosphere, and if you wanted to find life on this planet, you would look at the atmosphere on that planet or going around. And that's what you do with transit spectroscopy. Basically, you look at the planet's atmosphere when it is transiting its host star, right? And what you see in the atmosphere, hopefully, what you see are these more complex molecules. And does anyone recognize H2O? What's that? Water. CO2? CO. I have a chemistry class. All right, like yes. So if you have those more complex molecules, you could infer that there might be some life on the planet that is creating these gases and putting them out into the atmosphere of the planet. All right, so now we're going to look at a spectrum from the star. And if you've been reading your astronomy news, popular news, you will have heard of the exoplanet K218b, right? It's the hot planet that's out there right now. In the astronomy world, it's a hot planet. And the reason why it's a hot planet is because it has this molecule, right? Dimethyl sulfide, DSO. And DSO is really interesting because on Earth, the only thing that makes DSO are water-bound life, right? So algae and stuff in the water, right? And DSO is thought to be, by its density, a water world, right? So a planet, exoplanet covered with water. And if you're seeing DSO, and the only thing on our planet that makes DSO is life, we're inferring that there might be life on this exoplanet K218b, right? So how I like to think of, let's give me, of JWST, right, of this space telescope is less of, let me check. Okay, all right. So it's less of the eyes of an astronomer and more of the nose of an astronomer, right? So you're smelling, you're trying to smell the different molecules that could show you what life is or could tell you that there's life on that planet. Okay? All right. So I'm just give you a huge hint to what you should do up here, right? Exactly, because isn't life stinky, right? Parents, forgive me. But if you wanted to figure out if there's someone in a room, like what do people do that lets you know that they're in a room? All right, I'm not gonna say it, but we know what people do, and you can smell that they're in the room. Okay, so now as we come to our finale, right? I need one more person. Need one more little person to come up and be. You want to be the little person? I saw your hand first. What's your name? Matt? Huh? Madeline. All right, come on, Madeline. Come on. Come on. All right. All right. So I want you, Madeline, to look at the three different cups. So look at this first cup. You can take a little sniff. Does it smell like anything?
Yeah.
Kind of. All right. Now I want you to look at this one. Ooh, let's smell it. Ooh. Ooh. And then I want you to look at this one. Is there anything moving in there? You don't really see anything?
All I can see is bubbles floating.
Floating? All right. All right. So I'm going to show it to the crowd as well. So which one smells the stinkiest? You gotta sniff it.
Not that.
Not that one. All right. So you said not that one. This is Madeline. This is not me. See, people? Between this and this, give it another smell.
Okay. Feel like, yeah. Don't think it's any.
All right. Everybody give Madeline a big round of applause. Because Madeline just, let's go back. I love this slide. Because Madeline just sniffed out life. So there was life in the cup cup lettered B. So B was the life. I was very good at tricking you with A and C and keeping cup number B away. So yeah, so it was life in this cup. And what type of life do we think it was? Yeah, it's very simple. It's stinky. What do we use to make our bread at home? Yeast, yes. So it was yeast. And the yeast mixed really well with the sand that I have right here. So it made it very hard for people to see. But it was yeast. So B was the correct one. So it was yeast. It was the correct. It's not going on. All right. So as we finish up, so we know it's now B. As we finish up, I wanted to leave you with these takeaways. And they are that visual confirmation is not enough to see that life is there. We must observe changes over time. That's what happened in B. If you can see a little bit closer, you can see that stuff is floating around. It got a little cloudy once you got into B. And also biosignatures, such as smell, such as signatures of complex molecules, help you to see that there's life that exists in life that exists on an exoplanet. Okay. I will leave you. Oh, that's what we did. We're good. Okay, are we good with time? I wasn't watching the time, but yeah, we're good on time. I'll leave you with the slide. And this is one of my favorite slides. Please, parents, get your phones out. These are links, and this is on my website. These are links to different really cool astronomy resources for young people and older people alike. One of my favorites on here is Crash Course Astronomy, which is such a good resource for anyone that wants to learn more about astronomy. And also, is it there? Yes, the last one on the list, Planet Cosmo. For the younger people in here, I had a 3-year-old when I uh, discovered Planet Cosmo, and it's really good at teaching your younger ones about the solar system and also astronomy in general, right? So please go to the website and use the website to teach yourself and educate yourself more about astronomy and astrobiology. And with that, I will take questions. Okay. If I have any questions. Oh, I have a question in the back. Go ahead.
What happens with transit spectroscopy if the orbit of a planet is perpendicular to our view?
Then we don't do transit spectroscopy. Yeah, it's just not possible. Yeah. So that's a great question. So it's all about the orbital architecture of the planet with respect to our location, right? So if we don't have a transit, we can't use transit spectroscopy. What we're looking, oh, you know, I would say no. Can we use transit spectroscopy if it's not?
You can, if it's not in front of you,
Yeah.
that would start.
Yeah.
Also get signatures of the surface.
Yeah.
I kind of spectroscopy.
Yes, yeah. And then the next one that I was going to say is the gold standard that we really want to do is looking directly at the exoplanet and looking at the atmosphere of the exoplanet directly using spectroscopy, right? So actual planetary atmosphere, not transit, not looking at it using the star, right? So direct imaging of that exoplanet or the exoplanet's atmosphere. Yeah, but great question. Go ahead.
Okay, so just to, because I'm mathematically thinking this through. So
Mhm.
like if you were had like our solar system,
Yes.
and if you were here,
Yeah.
you would never see a planet, but you would see the sun itself through that wobbly thing.
Yeah.
So when
Yeah.
you were showing the radial
Velocity. Yes.
okay.
Yeah.
So you could use that to say, hey, there's probably something pulling that star.
Yes.
And then you would know to look closer.
Yes.
Because
And then
otherwise you wouldn't even know to point a telescope there, right?
you would not. No, you would not. Yeah. So yeah, you're right. That was more of a confirmation than a question, but I like it. I like the wheel spinning. Any more questions? Go ahead. Didn't have any smell? Oh, if the earth didn't have any smell, then probably we wouldn't be here, right? Like, so yeah, I think in and I should preface this with saying that smell doesn't equate life, right? So even with biosignatures, right, and the DSO, the dimethyl sulfide that I just showed you, it does not equate to definitely there being life on that exoplanet, right? We have certain things that are called abiogenic signatures, which means that abiogenic just means non-life signatures or non-life ways of producing those chemicals, right? And for example, sulfur. What is a non-biogenic or a physical way of producing sulfur on a planet? Volcanoes, eruptions, right? So you can get these chemicals in the atmosphere, not from life, right? So the the game for our astrobiologists is trying to not only find the chemical, but find the chemical in the right proportions with other chemicals that could say that there's life there, right? So it's a game of finding biogenic and abiogenic signatures and then trying to see if it's really life that's producing that signal. Okay, yeah. But great, see, you asked a question, had me going down this road. Lovely, yeah. Any more questions? Oh, you have a question?
We got some from online.
Oh, yeah, absolutely, yeah.
There's one from Juan Ramos. He
Yeah.
asked, is there a way to analyze the rotation rotations of exoplanets or planets in general? Night day cycles, and would they affect life?
Great question. So it depends, and I don't want to go down this road, but we will. We're going down this road. So so to first answer the question about night day cycles, yes, will have an effect on life. And one of oh baby, oh sorry, yeah, it's all right. All right. And one of the ways how it might affect is if you're too close in to your star. If your planet is too close into your planet will become something called tidally locked, right? Where only one side of your planet is going to be looking towards your star. Which is that good or bad? That's very bad. You don't want your thing to be looking directly at your star because it means that it's getting all the radiation and the other side is not getting any radiation. So you have a hot side, you have a cold side, and neither of those are typically good for life. However, you have this new great area of research, and I think it's cool, where you're looking for life on the terminator of the exoplanet, right? And a terminator just means the switch between light and dark, right? So we have a terminator on the moon, for example, right? So if you're going between that section of always sun or no sun, perhaps in that little strip, you might have the right conditions for life to exist on that exoplanet, right? So that is the answer to that part of the question. I don't even remember the first the rest of the question because I can you detect the rotation period of exoplanets? No, you cannot. You can a way how you could do that is what our gold standard, like directly imaging and looking at the planet, perhaps. But even then, it is a big it's a big reach for us. We don't have the technology yet. Keep funding us so we can see. We can hey, you know, keep giving us money. All right. Next question.
The next question is from Veronica Leahy. Are there things that JWST fails at when detecting exoplanets? As in, what improvements could a future space or ground-based telescope make on our current methods of exoplanets?
Not ground. That's the first thing. Let's keep it in space because our atmosphere is not very. It's not. It's not the best when looking at what you call it, looking at exoplanets, especially exoplanet atmospheres, right? Like it's not the. You don't want to do that. So take it off the planet, keep it in space. However, what JWST doesn't fail at. Let's rephrase that. What what we can improve upon is definitely having a larger mirror, right? It'd be more fantastic to have a larger area to collect those the the longer wavelength, right, or the photons coming from these exoplanets, right? So that would be fantastic. So basically, a larger space telescope that does very similar things to the JWST would be fantastic, right? That's what we'd love. Yeah. All right. Go ahead. Yeah. Go ahead. Go ahead. Yes, yes, we could do a star shield or a coronagraph, right? To like block out the star. That would be fantastic as well. It doesn't it have a small one right now? A big one around, yeah. From the spacecraft. You see, we're making ideas here. And all of these ideas also need what? Funding. So please continue to fund us so we can do this amazing research and keep educating folks like y'all about how we can find life outside of this planet because it's cool. All right. All right. And that is all the time I have for you. We're going to get this room dark and you all are going to see stars. All right. Are we ready? All right.
Okay, we're gonna have like a 2-minute break while the star computer
No, I was giving you